Suppose you want to know how many people need to be at a party so that you can connect any such three of the people so that they know each other, or that any such three of the people so that they don't know each other. Mathematically, this answer is calculatable and it's been found. But as you expand to needing 4 such people, or 5 such people, or even more to know each other or not know each other, it becomes more complex. So today we've brought the great mathematician Paul Erdös to bless us with mathematical facts. How are you, Paul?
Oh, I am pleased to be here.
Well, that sounds awesome. Let's get on with some maths.
We can explain this phenomenon using simplified mathematics, and only 6 points representing the 6 people at a party. One color, blue, representing people that know each other, and one color, red, representing people that do not know each other. Start this theory off at 1 point, representing one person. Now, since there are 5 other people that this person can have a relationship with, it is known that at least 3 of the 2 of these colors will be the same. So saying that at least 3 of the people that you know, in this case, will be people that he knows. So let's focus on the 3 that are actually the same color. I've already drawn it beforehand. Okay, so since we have these 3 that this one person knows, there's either a chance that at least 2 of these 3 people would have to know each other, thus creating a relationship with 3. And it doesn't even matter if the other person doesn't know that other person. We already have a relationship of 3 people that know each other. Or in the other case, where none of them know each other, it still forms a triangle of 3 points. Shaboom.
Essentially what we're looking for is a triangle.
Precisely, because a triangle represents a common relationship between 3 different people. Here's one possible combination of the 15 lines that connect all 6 points. And no matter how I draw this, there will always be at least one triangle formed. For example, I have made a red triangle right here. And I also see a blue triangle right here. Just a couple examples. 15 possible lines between all these points. You can deduce that the number of combinations of lines between the points is 2 to the 15th power, or in other words, 32,768 different ways that all these points could be connected. Just a connection of 3 different people. Let's just say, for example, that you want to have a connection between 4 different people. In this case, you need 18 different points with various connections. In this case, for the 18 points, there are a total of 2 to the 153rd possible ways you can draw the lines between all 18 points.
So how many people are needed to find 5 such people?
Thing is, the solution has not been found yet. For right now, the points in order to discover this would be between 43 points to 55 points. And there are a total of 10 to the 447th power possible combinations that you can make out of these points.
So it's not likely we'll find it anytime soon?
Not by ourselves, no.
So Paul, what do you think this tells us about math, or even about humans today, and why is it important?
Well, this theory is important for 2 reasons. The first reason shows that even with the advancements of technology in our day and age, it's still possible that we have unanswered questions in mathematics. The second reason of this theory is to prove that no matter how random any set of points may appear, it proves that there is a set correlation or pattern present in the points, proving that all complete disorder is not possible in this world.
So Paul, tell me a little bit about yourself. It's been such an honor to have you on here, and I just want the viewers to know a little bit about you.
Well, the viewers must know. Ever since I've been a child, I've loved math. My parents both being mathematics teachers, I just had all the textbooks around me, read them every day, and numbers became my friend. Especially prime numbers, they're the realest. Anyways, as I grew up, the young age of 17, I was admitted into the Péter Pázmány University in Budapest, where I got my PhD in mathematics in 4 simple years. From then, I began to work on many papers, probably the most published mathematician out there. And there's now a number called the Erdös number, where people, if they write a number with me personally, they get the Erdös number 1. And if anyone writes a paper with that person who writes a paper with me, they get the Erdös number 2. Currently, the highest record is Erdös number 15. So, I mean, I have pretty long stretching length going out there, guys.
So you've grown up with mathematics, and mathematics has almost conformed to you.
Pretty much. I mean, don't mean to brag or anything, but I'm pretty much a big deal.
So what part of a daily life does mathematics play for you?
That is my life.
That is your life?
Yes.
You don't own a house, do you?
You know, I move a lot, so I wouldn't really call anything a house or a home, but
You more call mathematics your home?
yes,
Okay.
my livelihood.
Your livelihood, okay.
Yes.
So thank you, Paul.
Oh,
It's a
quite
pleasure to have you on today.
Lovely to be here.
Thank you for blessing us with your mathematics.
Bless
I hope we
up.
can work again together.
Mm-hmm.